is the topic of gas transport. And gas transport refers to the way in which oxygen and carbon dioxide are transported in the bloodstream from the lungs to tissues and then from the tissues to the lungs and throughout the body. So starting off with oxygen transport. Oxygen is carried by the blood in two ways. It is carried physically dissolved into the plasma and chemically bound to hemoglobin. Now, the oxygen that's physically dissolved into the plasma is represented by plasma PO2. So the partial pressure of oxygen of the blood, which is really the partial pressure of oxygen in the plasma, directly measures the amount of oxygen that is physically dissolved in plasma. The amount of oxygen that's chemically bound to hemoglobin is represented by something called the hemoglobin percent saturation. And we'll talk about that more in a little bit, but that's basically the percentage of hemoglobin in a volume of blood that is saturated with oxygen. Okay? So hemoglobin percentage saturation is the percentage of hemoglobin in a volume of blood that is fully saturated with oxygen. So between these two, far more oxygen in a volume of whole blood can be found chemically bound to hemoglobin compared to physically dissolved in plasma. And the reason for that is that oxygen is a relatively nonpolar molecule. Molecular oxygen, written as O2, is a fairly nonpolar molecule. And so it doesn't really dissolve very well in plasma. So only about 1.5% of total blood oxygen can be found physically dissolved in plasma. Okay. The other 98+% of oxygen that's found in blood is going to be found chemically bound to hemoglobin. So if we go back to this, these two measurements, plasma partial pressure of oxygen, or plasma PO2, versus hemoglobin percent saturation, keep in mind that whenever we look at the PO2 of blood, what we're really looking at is about 1.5% of the total oxygen in that blood, and the other 98+% is chemically bound to hemoglobin and can be will be reflected by the hemoglobin percent saturation. So let's talk a little bit more about hemoglobin. Hemoglobin is a large intracellular protein found in red blood cells, and hemoglobin is highly specialized for oxygen transport. And as we'll see as we go through this section, it's very, very well suited for its job. Hemoglobin is composed of 4 subunits, each with an iron-containing heme group. These heme groups that contain iron represent the binding sites for molecular oxygen. So each heme group can reversibly bind one oxygen molecule. Okay. So then in one hemoglobin molecule, with 4 heme groups, you can carry up to 4 molecules of oxygen. Okay. And when a hemoglobin protein is carrying 4 molecules of oxygen, we describe that hemoglobin as being saturated. So when hemoglobin is not bound to oxygen, we call it deoxyhemoglobin or deoxygenated hemoglobin. And when hemoglobin is bound to oxygen, we call it oxyhemoglobin or oxygenated hemoglobin. So the hemoglobin protein, this is what we're looking at here. You can see that there's 4 subunits. The upper chains we refer to as beta chains. The lower chains we call alpha chains. And you can see at the center of each of these subunits we've got this heme group that contains iron. Okay? So the 4 molecules of oxygen will be bound to these iron containing heme groups. So the main factor that is going to determine the extent to which hemoglobin binds to oxygen is the partial pressure of oxygen in the plasma. So the PO2 of plasma is going to be the main factor that determines binding of oxygen to hemoglobin. Okay. When all 4 binding sites on hemoglobin are occupied, hemoglobin we describe as being fully saturated. And this percent hemoglobin saturation, which remember is the percentage of hemoglobin in a volume of blood that is saturated with oxygen. Okay. So this measurement, percent hemoglobin saturation, is determined by the PO2 of plasma. Okay. And this relationship is really simply a matter of mass action, meaning that hemoglobin in the presence of oxygen tends to form oxyhemoglobin. Okay. And when O2 levels decline, oxyhemoglobin tends to unbind oxygen. Okay, so this is a reversible reaction. So the extent to which hemoglobin is going to bind to oxygen is going to depend on how much oxygen is there. And that is why PO2 of plasma determines hemoglobin saturation. Because how much oxygen is there, really it represents how much is in the plasma available to bind to hemoglobin. Okay. This relationship between the PO2 of blood and the percent hemoglobin saturation is not a linear relationship. Okay. So the PO2 of blood determines hemoglobin saturation, but that is not a linear relationship. So let's look at what it actually looks like. So what we're looking at here is something called the hemoglobin dissociation curve. And this actually depicts the relationship between percent hemoglobin saturation on the y-axis and the PO2 of blood on the x-axis. So the red line represents this relationship, and if it were a linear relationship, this red line would look like a flat line of some particular slope. Okay. However, this red line is actually described as being a sigmoid curve, right, which is kind of an S-shaped curve. So this is really the relationship between the PO2 of blood and the percent hemoglobin saturation. And so what we see is at the lower levels of blood PO2, okay, at the lower levels of blood PO2, the slope of this relationship is much more steep, okay, compared to the upper levels of blood PO2. Okay. So the slope of the line at the upper levels of blood PO2 is more flat compared to the lower levels of blood PO2, where the slope is more steep. Okay. And so a flatter slope versus a steep slope, what that really means is when the slope of the line is steep, like we see between 0 and, let's say, 40 or 50, okay, when the slope of the line is steep, that means that for any change in PO2, any increase or decrease in PO2, that results in much larger changes in percent hemoglobin saturation. And so let's look at what that looks like. If we go from 10 millimeters of mercury in blood PO2, and we move just 10 up the scale, so we go from 10 millimeters of mercury to 20 millimeters of mercury. At 10 millimeters of mercury, hemoglobin is 10% saturated, right? At 20 millimeters of mercury, hemoglobin is a little over 20% saturated. So it's doubled in saturation, going just 10 millimeters of mercury. If we, however, look at the other end of the spectrum, we look at going 10 millimeters of mercury, going from 90 millimeters of mercury to 100, what we see is that we barely get any change in percent hemoglobin saturation. At a PO2 of 90, the percent saturation is around 95, and at 100, it's only going up to, let's say, 98, 99. So you're talking about 2, 3, 4% change versus a 10% change. So very, very small changes at the flatter region, at the upper range of blood PO2 compared to the lower range of blood PO2. So that difference in the relationship is highly adaptive for a hemoglobin's job, because hemoglobin is responsible for in the lungs, when exposed to oxygen coming in from the alveolar space, hemoglobin's job in the lungs is to load up on oxygen. It's to bind to oxygen. Okay? And as it then leaves the lungs, goes into systemic circulation and interacts with systemic capillaries and tissue, hemoglobin's job there is to do the opposite. It's to let go of oxygen. Okay? And so if we look at this flat portion of the curve versus this steep portion of the curve, what we're actually looking at are ranges of PO2 that reflect these two different settings. So in the upper portions of blood PO2, right, from 100, 90, 80, this is the range of PO2 that hemoglobin will experience when it enters the pulmonary capillaries. Okay? And in this range of PO2, hemoglobin binds to oxygen readily, and it binds to it very tightly. Okay? However, when that hemoglobin becomes fully saturated, it gets to that blood becomes fully oxygenated. Okay, now that hemoglobin and that blood moves out of the pulmonary capillaries, right? It goes back to the heart, and then goes on to systemic circulation. The PO2 at systemic capillaries is more like 40, right? Maybe even a little bit lower, depending on how metabolically active the tissue is. At that range of PO2, hemoglobin, even at small changes, starts to let go easily, let go of oxygen very easily. Okay? If we went from 40, a PO2 of 40 to a PO2 of 30, you're talking about letting go of going from a hemoglobin saturation of, let's say, 75 to a hemoglobin saturation of 60. Right? So you're talking about hemoglobin letting go of a significant amount of oxygen, right, even for small changes in PO2. Okay? So this is one of the many reasons why hemoglobin is so well adapted for oxygen transport in our body, because under conditions of high PO2 in the pulmonary capillaries, it binds to oxygen very tightly and doesn't let go. And then in the systemic capillaries, where the oxygen levels are lower surrounding the hemoglobin molecule, it readily lets go of oxygen. It has a very much looser hold on oxygen. Okay. This relationship between the PO2 of blood and the percent hemoglobin saturation, the PO2 of blood determines the percent hemoglobin saturation, but that relationship can actually be influenced by several factors. And these factors all reflect, the ones that we're about to talk about right now, they all reflect the degree of metabolic activity in the body and locally in tissue. So the local CO2 concentration can affect the relationship, can affect this curve. The local pH, or degree of acidity, can change it, and the local temperature. So when CO2 levels are high right? That reflects a higher rate of metabolism, so more metabolically active tissue. So you can have a tissue bed, let's say a particular skeletal muscle group that's working very hard. It's going to have a local concentration of CO2 that's a little bit higher than the rest of the body. Okay. It also is going to have a local pH that is more acidic. Right? The value of the pH will be less and it will be more acidic because it, among other things, it's producing lactic acid. And then also because whenever metabolism increases, we're actually producing more heat. The local temperature will be higher as well. So under those conditions, let's say in this muscle group, it's highly metabolically active, CO2's higher, it's more acidic, temperature's higher. Under those conditions, what we see in the relationship between PO2 and hemoglobin saturation is what's described as a right shift of the curve. Okay? So high CO2, high acidity, high temperature causes this relationship to shift to the right. Now what that means is, and so let's just focus on this lower end of the spectrum because that's what's relevant for this example, because that's the systemic capillary level. It means that at any PO2, this new shifted curve is going to have a lower hemoglobin saturation than the original curve. So not only is hemoglobin naturally letting go of oxygen at these lower levels of PO2, when a tissue bed has these indicators of high metabolic activity, hemoglobin lets go of even more oxygen, right, at that local tissue bed. Okay. And so in this way, hemoglobin is delivering more oxygen to the tissues that actually need it the most because they are more metabolically active. Now the flip side is also true. Let's say you have a muscle group that actually has not, that has very, very low activity. It's at rest and it's been at rest for a prolonged period of time. In that tissue bed, you might actually see a local decline in metabolic activity, and so CO2 levels get a little low. The acidity gets a little low, so it is less acidic than normal. The temperature might even get a little cooler. Under those conditions that indicate very low metabolic activity, that shifts the curve to the left, okay? Which means that hemoglobin, when it enters the capillaries feeding that particular tissue bed, will tend to actually hold on to oxygen, right, rather than give it up. Okay? So that the hemoglobin saturation at the same PO2 compared to the original line is actually slightly higher. Okay? So hemoglobin saturation remains slightly higher in that tissue bed because it doesn't let go of oxygen. And really that's because this tissue doesn't really need it. Okay? So hemoglobin, as I said, is very, very well suited for, or it's very, very well adapted for its job of oxygen transport, because under normal conditions it will tend to hold on to oxygen when it enters the lungs and then let go of oxygen at the level of systemic capillaries and the tissues. And it will tend to deliver more oxygen, even more oxygen, to the tissues that need it the most, and less oxygen to the tissue that needs it the least. So what about carbon dioxide, carrying carbon dioxide in the blood? When CO2 enters the blood from tissues, it's carried in three ways by the blood. CO2 can physically dissolve in the bloodstream, and that's about 10% of total CO2. So CO2 is actually a little bit more polar, and so it's a little bit better at physically dissolving into the plasma. And again, the amount of CO2 in the plasma is represented by the pCO2 of plasma, the partial pressure of CO2 in plasma. Another 30% is actually bound to hemoglobin, but it's not competing for the oxygen binding sites. Okay? CO2 instead binds to the globin or the protein portion, not the heme groups. Okay? However, when CO2 binds to hemoglobin, it actually reduces hemoglobin's affinity for oxygen. So when CO2 binds to hemoglobin, hemoglobin is more likely to let go of oxygen. And that relationship is referred to as the Haldane effect or the Bohr effect. That as CO2 binds to hemoglobin, it tends to promote the unbinding of oxygen. Okay? And that relationship is actually part of the mechanism that we talked about here, that as CO2 levels rise, hemoglobin is tends to let go of oxygen. Okay? And the mechanism for that is CO2 binding to hemoglobin, causing hemoglobin to let go of oxygen. The last form that we see carbon dioxide in the bloodstream is in the form of a weak base called bicarbonate, which also can form a weak acid called carbonic acid. Okay? And 60% of blood CO2 is carried in this way. Now, CO2 has to enter blood cells and interact with a particular enzyme in order to form bicarbonate carbonic acid. Okay, so let's look at what that looks like. So CO2, so what we're looking at, this big red circle, or oval rather, is meant to represent the red blood cell, and CO2 over here is sitting in the plasma. Okay? And so this is the amount of CO2 that's physically dissolved in plasma, which is measured by the pCO2. CO2 diffuses across the red cell membrane, and in the presence of water and a particular enzyme called carbonic anhydrase, CO2 will form H2CO3, which is carbonic acid, and carbonic acid ionizes into free hydrogen and bicarbonate. Okay. So this is happening in the red blood cell, okay? And when this happens, and you can see this is all reversible, okay? When this happens and you have the formation of carbonic acid and then the ionization of that, the bicarbonate is going to exit the cell and get into the plasma. The hydrogen ions are also going to exit the cell and get into the plasma. Okay? And we're not showing the way in which these hydrogen ions get out of the cell, but they do. Okay? The bicarbonate gets out of the red blood cell through an exchanger with chloride. So HCO3 is, and with this exchanger, this is a secondary active transport exchanger. Okay? And the direction of this exchanger is entirely dependent on the HCO3 concentration gradient. So as HCO3 is formed, right, when HCO3 levels inside the cell increase, you then start to get the passive movement of HCO3 out of the cell, and that energy that's released actively pumps chloride in the opposite direction. Okay? So when CO2 levels rise in the blood, okay, so CO2 levels rise in the blood when blood is relatively deoxygenated, right? It's leaving tissues and it's headed back to the heart and the lungs in order to get oxygenated. So when CO2 levels in the blood rise, the pCO2 of plasma rises, CO2 starts to move into red blood cells, it interacts with carbonic anhydrase, it forms a carbonic acid, that forms hydrogen ions that leave and enter the plasma, and HCO3 that builds up and flows out of the red blood cell into the plasma, pulling chloride into the cell. Now, when this unit of blood, when this volume of blood finally reaches the lungs to get oxygenated, it's also going to start to expel CO2. So when this unit of blood enters the lungs and the CO2 starts to leave the plasma, okay, so the CO2 starts to leave the plasma, the PCO2 starts to drop. Now you get less of this forward reaction, and you actually start to get more of this reverse reaction. Okay? So you get less of this forward reaction, which means that you're not forming HCO3, right, at the same rate. Intracellular HCO3 levels start to drop. The direction of the concentration gradient for HCO3 switches. Now, I know it's not drawn, but now HCO3 moves into the cell through the exchanger. The exchanger starts to work in the opposite direction. HCO3 starts to move into the cell through the exchanger. Chloride gets pushed out, and then HCO3 goes through this. As it builds up, it starts to move in the reverse direction. It combines with hydrogen ions, it forms carbonic acid, and then it then converts to water and CO2 moves out. Okay. So in deoxygenated blood, you have the favoring of the forward reaction. Right? In deoxygenated blood, as CO2 climbs in the plasma, you get the forward reaction and the movement of HCO3 out. And in oxygenated blood, as CO2 is getting removed and PCO2 drops, you get the reverse reaction. HCO3 goes into the cell and goes through the reverse reaction, forming CO2 and leaving the cell. Okay. And this tendency for chloride to get pushed back and forth into and out of the cell, depending on the HCO3 concentration gradient, is sometimes referred to as the chloride shift. It's not very significant for our purposes, but it's just something to be aware of.